You've built a powerful teacher model. It's accurate, it generalizes well, and every single inference call is costing you a small fortune, so you decide to distill it into something leaner. Smart move. But here's what nobody tells you up front. The distillation process itself can burn through your compute budget just as fast as running the teacher in production, if you're not careful. In this video, I'm going to walk you through the specific strategies that actually move the needle when you're running large-scale distillation projects. Not generic advice, concrete techniques with the trade-offs you need to know before you commit. Just to set context, when I say large-scale, I mean scenarios where your teacher model has 7 billion parameters or more, your distillation dataset runs into hundreds of millions of tokens, and your student training spans multiple GPU nodes over days or weeks. If you're doing a small LoRa distillation on a single A100, some of this still applies, but the ROI on these optimizations really shows up at scale. The cost drivers in distillation are the same three you always fight: teacher inference to generate soft labels, student forward and backward passes, and data throughput, reading, tokenizing, batching. Let's go through how to attack each one. The single highest leverage move most teams miss: decouple teacher inference from student training entirely. By default, many distillation pipelines run the teacher forward pass online, meaning every training step, you're paying for teacher inference on that batch. If you're doing 10 epochs, you're running the teacher 10 times on the same data. That's 9 wasted runs. Instead, run the teacher once over your entire dataset, serialize the output logits or probability distributions to disk, and load them as static training targets during student training. You've just cut your teacher compute by up to 90%. The trade-off: storage. Full logits for a large vocabulary over a big dataset can run into terabytes. You have two options here. First, vocabulary pruning. Instead of saving all 32,000 plus logits per token, save only the top K, typically the top 50 to 200. The long tail of near zero probabilities contributes almost nothing to the KL divergence loss anyway. Second, quantize the stored logits. Float 16, or even int 8, is usually sufficient for training signal. You don't need float 32 precision in cached soft labels. Combined, these two tricks can reduce your logit storage by 95% or more, making this approach practical even at scale. More data is not always better in distillation.